Albert Einstein's general theory of relativity gave rise to radical revisions of our view of reality in terms of the large-scale structure of the universe. But the period also saw a revolution in how we think of the small. Today it seems common sense that the world is comprised of atoms. The 19th century German philosopher Friedrich Nietzsche said that when a revolution triumphs completely, it becomes invisible. So it is with the atomic paradigm. It would never occur to us to question the existence of atoms, and it strikes us as odd that anyone would doubt it. But in the 20th century, the ranks of the anti-atomists included people like Wilhelm Ostwald, the Latvian chemist who won the Nobel Prize in 1909, and two of the men who were Einstein's personal heroes and forefathers of the theory of relativity, Ernst Mach, the Austrian physicist and philosopher, and Henri Poincaré, the French physicist and philosopher, considered one of the greatest mathematical minds to ever walk the earth. Why would such geniuses doubt the atomic hypothesis? And what evidence swayed scientific consensus? How did our view of matter change at the start of the 20th century, and what effect did it have on our culture? These are the questions we'll chat about now. Now, one of the interesting elements of this story involves the sociology of science. We often speak of science as a unified endeavor, right? Scientific consensus is this. Scientists tell us that, right? We think, sure, there's passionate division at the cutting edge, but things get settled and scientists are one big happy family about pretty much everything else. But the scientific world is a divided one. You have different fields and subfields, which are their own self-contained communities with different methods, intellectual commitments, and power structures. The story of the atomic hypothesis at the turn of the 20th century is interesting because it pits two different scientific communities with contrasting paradigms against each other. The physicists, on the one hand, deal with the behavior of material things. So, they saw the question of the ultimate constitution of matter as part of their bailiwick. The chemists, on the other hand, concern themselves with properties of substances and the ways they're affected by interaction. To them, this question is well within their jurisdiction. Part of what we have is a question of intellectual ownership. Whose question is this? When we ask about the structure of matter, who should be considered the experts? Now, the worst arguments are often those within a family. Fights with strangers can be nasty, but when long-standing insults and insecurities underlie the point of contention, look out. And that's what happened here. Physics was the older sibling, cocksure with a sense of entitlement, looking down on chemistry as the less developed and less rigorous. Chemistry, on the other hand, thought that physicists were being their typical sloppy selves, rushing in and talking when they don't really know what they're talking about, not understanding the real complexity of the matter. There's a joke that chemists love to tell about physicists. So, this farmer wants a new chicken coop and wants to figure out what shape and size he needs in order to maximize the number of chickens he can house. He finds an engineer, but the engineer wants too much money to figure out the problem, so he goes to his brother-in-law, a physicist. The physicist comes out, takes measurements, writes things down, and says, "Give me a week to make some calculations, and I'll get you the dimensions." A week goes by, and the farmer visits the physicist. Proudly pulling out a sheet of paper, the physicist says, "Well, assuming spherical chickens." Physicists are famous for their simplifying assumptions. This is not a weakness in physics, but a necessity. Once Newton gave the world calculus, physicists were able to translate real-life problems into their mathematical language, which could generate exact solutions. The problem was that the messy real world was often too messy to translate completely. The math would be too hard, or the language couldn't quite capture all of the aspects of the real-world system. So, the standard move was, and still is, create a simplified mathematical model that resembles the actual system in the most important ways. One of these goes back to Newton himself. When we think of two things bouncing off each other, say billiard balls on a pool table, the case is complicated if the ball has shape and size, especially if the shape's not perfectly round. So, physicists begin by taking the object as if it's what they call a point mass. That is, a thing with no shape and all of its mass focused at a single dimensionless point. Once they get that case understood, they get ambitious and give the mass a shape, but it's generally spherical, perfectly round, so there's symmetry to work with. In this situation, we don't have to worry about orientation or the effects of bumps or corners, which make the calculations in many cases impossible to write down or solve. Since the point mass is a standard way of thinking in physics, the atomic hypothesis, that the world is really at its most basic level just a bunch of joint point masses, was something they were naturally comfortable with. It wasn't only their usual approach, but justified the claim that their field had priority over the question at hand. Chemists, on the other hand, by and large, hated the idea of atoms. Not just because the idea reduced chemistry to physics, but because of the chemist's own history. When people work hard, struggle, and sacrifice to make something out of themselves, they're justifiably proud of the person whom they've become. But it's often the case that they're somewhat embarrassed about where they come from, about their earlier identity when the journey started, about some of the mistakes they made, about some of the immature phases in life they went through. They deny any attempt to identify them with their past in order to justify their present. This was the case with chemistry. Now, chemists through the 19th century were proud of their place as real scientists and bristled at any mention of chemistry's intellectual heritage found in alchemy. Today, the term alchemy is itself an insult in scientific circles, evoking ideas of magic and supernatural powers. But alchemy, in its heyday, was real science. How alchemy went from being a highly respected endeavor to one that makes chemists bristle is itself an interesting story. Now, words like alchemy that start with al, right? Like Ptolemy's book Almagest or algebra or Alka-Seltzer or Al Gore tend to come from Arabic, in which the word al means the. Alchemy comes from the Greek words al and the Greek term chemia, the transmutation of metals, which was taken by Arabic speakers in North Africa and turned into alchemia, which became alchemy. The transmutation of metals, not just creating gold, which is what we think of when we think of alchemy, it was the study, in general, of metallurgy. We often fail to understand how important metallurgy was to the development of human history. Now, about 7,500 years ago, humans figured out how to extract copper from ore, rocks they found. The ability to make tools out of metal allowed for rapid technological advances and a substantially better quality of life. It also made extremely effective weapons that allowed for domination over those who did not have access to the substance. 4,300 years ago, the discovery was made that a much harder metal was formed if tin was added to the copper, forming bronze. This gave even greater advantages to those with the know-how. When the metallurgic advances led to the ability to create tools and weapons out of iron 3,200 years ago, the practitioners became essential to developing and maintaining political power. If you wanted to be a king, you needed metallurgists. They were the key to your continued power. The study of alchemy incorporated a number of cookbook recipes for making different substances by heating, cooling, combining different substances, weighting, and mixing. And, as with all scientific endeavors, theories were developed to explain and predict. These theories were tested, and new developments were made. If alchemists could make metal used in weapons, maybe they could also make metal used to buy them. Gold and silver seemed a reasonable hypothesis, and one that would make alchemists themselves wealthy. So, much effort was expended in the project, and alchemists themselves would play it up to make sure their positions and funding were maintained. The alchemists had a prestigious, well-paid job, but to keep it, they had to make sure that not everyone knew how to do what they did. So, they developed a shorthand, a code in which to write down their methods and results. They selected characters and names for substances. So gold was the king, silver was the queen. The various chemical processes were disguised in terms of human interactions, fighting or marrying. And thus, the recipes for creating desired chemical reactions became stories. This was meant to protect their jobs by keeping their craft under wraps as proprietary knowledge. But Eventually, the elements of the code were given supernatural significance. The mystery that was intentionally generated by using obfuscating terms was taken as mysterious for occult reasons. If you needed to wait a set amount of time before proceeding from step 5 to step 6, find a poem to recite that takes that long. But what happened was that the poem was given magical powers. The words were thought of as responsible for the change, not just the time lapse that was the original purpose. And so, alchemy went from a study of natural magic, that is, the ability to create changes from things in nature, to what we now think of as supernatural magic, a door to powers beyond nature. This episode in the history of chemistry was a sore point for generations. Chemists were sensitive about their status as rigorous researchers who do real science. Science is empirical and chemistry is a science, so chemistry will only deal with that which can be observed, that which can be measured. Of course, those observations and measurements were trending in a direction. For the 2,000 years after the high point of classical Greece, Aristotle's chemistry ruled supreme. We had earth, water, air, and fire, and they were combinations of the fundamental properties hot, cold, and dry, wet. When you mixed combinations in appropriate ways and subjected them to various conditions, we could create new combinations in well-documented, predictable ways. Leucippus and Democritus had advanced the atomistic picture of the world at the time, but it was rejected. The word atom comes from the Greek atom, or uncuttable, because atoms were thought of as indivisible particles bouncing around in a void. That was the reality of the ancient atomists, but, that the world is filled with bits bouncing around in nothingness, but no one had ever seen these little bits, nor could the atomists provide any way to get to them. The nothingness seemed to be filled with air, which certainly did not appear in any reasonable way to be anything but continuous. And no matter how small a thing is, there seemed to be no reason to think we can't cut it in half, and cut that in half, and cut that in half. Classical opponents threw a range of objections at the atomists, and their account seemed no more explanatory than Aristotle's. In the 19th century, there was an added problem that any theory which bases its view of reality on invisible little particles responsible for observable particles moves the entire field back to the realm of alchemy, back to a place where what chemists would be talking about was beyond their power to see. Atoms were seen as a form of magic. While the Aristotelian physics fell apart with Newton's mathematical principles of natural philosophy in the 1670s, the chemistry would hang on. The first major blow came with the discovery of oxygen. Joseph Priestley, as his name would have it, was a member of the clergy. He was a minister in a splinter group of rational dissenters who eschewed mysticism and believed that the universe was created by God with an organized structure that could be completely understood through the rigorous use of the human mind. As such, he dedicated himself to its careful examination, at first working on questions of electricity, which brought him into discussions with Benjamin Franklin, who was visiting the continent. This connection would eventually lead Priestley to come to America. But before that move, he found himself in England, living next door to a brewery. Now, for many of us, this would be a wonderful thing, for reasons quite different from those of the good minister. For Priestley, the brewery was a fascinating place full of what we now think of as standard tools for chemistry, largely because of the way Priestley used them, not to brew beer. Now, the brewing process is intricate and fascinated Priestley, especially when he looked at the air surrounding the grain that was fermenting. Recall that for Aristotle, air is an element. It's a single thing. There is one kind of air. What Priestley was able to do in his experiments in conjunction with the brewers was to isolate some air that had different properties from normal air. So if you had a burning piece of paper, you could pump in some of this, what he called fixed air, and the flame would extinguish. If you put a mouse in a bottle and filled it with fixed air, the mouse would die. He found another kind of air, dephlogisticated air. And if you put out a flame and then pumped in dephlogisticated air, the flame would return. More amazing is that if you pump dephlogisticated air into the bottle, the mouse would come back to life. But only if you did it in time. Dephlogisticated air is what we now know as oxygen, and fixed air is what we now call carbon dioxide. Priestley not only isolated carbon dioxide, but figured out how to mix it into water. This makes him not only the discoverer of oxygen, but the inventor of soda. All in all, Priestley was able to create many different kinds of air, and this created a serious anomaly for the Aristotelian system. Right? It set off a rush with scientists finding more and more substances which were experimented upon. It was found that some substances combined with others and could be derived from others, but could never be broken down any farther. Earth, air, and water turned out to be combinations of these more basic elements. The list grew of elemental substances throughout the 19th century. This meant that a new, non-Aristotelian basis would be needed to account for the observed behaviors. The big breakthrough came with the work of John Dalton, the British chemist, and the French researcher Joseph Louis Proust, who independently discovered that whenever you combine elemental substances to form combinations, there's a fixed ratio of what you need to put in order to get out a given amount. When we account for the relative weights of the stuff going in, the ratio of the amounts of stuff in to get 1 unit out is always a ratio of counting numbers. It's always a simple 2 to 1, 3 to 1, 4 to 1, right? That sort of relationship. Now, if nature's using counting numbers, it's probably counting something. And you can't count something unless there's something to be counted. Maybe these elemental substances are made up of countable bits. Chemists were nervous that atoms were making their way back. Work on gases seemed to be a safe place on which to ground chemistry as a real science. In the laboratory, we could measure macroscopic properties like pressure, temperature, volume. When we related these, we were connecting observable properties with other observable properties in testable patterns. It was straightforward, unobjectionable, vanilla science of the most respectable sort. Gas laws were formulated and celebrated. Boyle's law connected volume and pressure. Charles's law connected volume and temperature. Gay-Lussac's law completed the circle and connected temperature and pressure. Nothing objectionable here. Until the entrance of the Italian chemist Amedeo Avogadro. Avogadro was an atomist. He contended that the work of Dalton and Proust showed that when we combined fixed ratios of elements and created an integer's weight of a new substance, it was because there were basic building block type things joining with other basic building block type things to create the complicated hybrid things. He called the bits of the elements atoms and labeled the combinations molecules. Before Avogadro, the usage of the two terms was random, but following, there was a clear image. Avogadro proposed that equal volumes of all gases at the same temperature and pressure have the same number of molecules. Before Avogadro, we could take the idea of atoms as a heuristic, as a way of thinking, which gives us an easy image to hold in our mind. But make sure, many chemists said, that you don't mistake the mental picture for reality. But it was Avogadro who took the next step and introduced the number of molecules. You can't have a number of things without having those things. Avogadro did not take the next step and find the number of molecules in a mole of a substance because those concepts didn't exist yet. But it was his bold step that made them possible. When Avogadro's law was added to the other gas laws, it was now possible to write down a new combined law known as the ideal gas law, which says that for any gas, the pressure times the volume is proportional to the number of molecules times the temperature. The chemists had created this law, and now the physicists were about to take over. In 1873, James Clerk Maxwell, one of the most important figures in the history of physics, published a paper called Molecules. In this paper, he derives the ideal gas law from a mechanical picture of gases. He says, let's think of a gas as if it were a collection of atoms. Now, he's a physicist, so when he says atom, what he tells us is he's assuming something perfectly round, infinitely hard, that has no electrical charge, and is only affected by other atoms by knocking into them. We're back to the physicist's habit of assuming spherical chickens. But in making those assumptions about an underlying reality, what comes out is the ideal gas law, a testable statement about the macroscopic properties of pressure, temperature, and volume. It would be a coincidence of epic proportion if that law accidentally fell out of the atomic picture. Everything in the results is macroscopically measurable, except one thing: the number of molecules. The anti-atomistic chemists who were taking atoms to be just a helpful way of thinking but not really real would have to say that it was a lucky but meaningless occurrence that assuming atoms generates a world that behaves exactly like this one. From Avogadro's work, it follows that the number of the molecules in a mole of the substance is a fixed quantity, which was given the name Avogadro's constant or Avogadro's number. To determine Avogadro's number would be to make a statement about the reality of atoms. Physicists like Albert Einstein and the Nobel Prize-winning French experimental physicist Jean Perrin became serial derivers of Avogadro's number. They found it everywhere. It popped up when you studied gases. It popped up when you studied liquids. It popped up when you studied alpha particles. It popped up when you were studying cathode rays. It was there when studying heated bodies. It was like a scientific stalker. Everywhere you went, Avogadro's number could be found around every corner. In his doctoral dissertation in his first major paper, Einstein proposed a way to experimentally determine Avogadro's number, but ended by saying that it would be very difficult to do. Jean Perrin took up the challenge and through painstakingly delicate work determined Avogadro's number and showed it to be a constant across many different situations. Perrin's work was so good that finally, even the most strident anti-atomistic chemists cried uncle, and atomism became the scientific consensus. So far, this has seemed like a purely in-house conversation pitting physicists against chemists. But we see the effects leaking out beyond the purely scientific community. It's the high point of this debate, just as the atomists are starting to achieve the upper hand, that we see pointillism emerge in modern art. For painters, the traditional basic unit was the brushstroke. Painting is a smooth medium. They studied with masters who taught them proper brush technique. Paints were mixed on a palette so that you could continuously blend in new colors, so the paint applied to the canvas smoothly flowed from one shade to the next without harsh contrasts. Nature was smooth, and so must be its representations in art. But in the 1880s, as the modern concept of the atom was exciting leading-edge minds in the scientific world, figures like Georges Seurat, Paul Signac, and Vincent van Gogh were challenging the received view in painting. For them, the representation of the world would be made up of individual dots of color, each completely distinct from its neighbors. Nature is not smooth, and neither would be the depiction of it. Up close, it was comprised of nothing but self-sufficient dots, atoms of color. But step back and look at the whole, suddenly the properties emerge. We see atomism in art as well as in science. But these weren't Democritus's atoms. They were not uncuttable building blocks of the Greeks. No, they were more complicated. In 1897, the British physicist J.J. Thomson discovered that the cathode rays physicists had been investigating were really negatively charged particles, what we would come to know as electrons. Eventually, we realized that they were pieces of atoms that were capable of being stripped out. Atoms had parts. Atoms had structure. Since the atoms were electrically neutral and the electrons were negative, there had to be a positive part of the atom to balance out the electron. But we didn't seem to have a positive correlate to the cathode ray, so Thomson proposed what came to be known as the plum pudding model of the atom, in which the atom was a smear of positivity, that's the pudding, with the electrons as little negatively charged nuggets inside of them, that's the plums. This went by the boards with the work of Ernest Rutherford, a New Zealand-born physicist who relocated to Cambridge, where he was seen as a true Tasmanian devil. A big man with a walrus mustache. He had a big booming voice and a bigger booming laugh that would forever enter the lab, singing "Onward, Christian Soldiers." Despite lacking pitch, rhythm, and concern about what others thought about him or his lack of vocal acumen. Rutherford and his assistants, Hans Geiger and Ernest Marsden, were conducting an experiment, shooting alpha particles at very thin sheets of gold. Marsden had the unenviable job of spending hour after hour in the dark, writing down where the alpha particles landed. The particles penetrated the foil and a spark on a phosphorescent screen around the equipment, and it was Marsden's job to keep track of the angles at which the particles were deflected. Most of them suffered very little deflection at all, but occasionally there would be ones that not only had their trajectory bent a little, but actually bounced backwards. This was bizarre and unexpected. It was so infrequent that it could have been written off as Marsden's eyes playing tricks, given long hours of concentration he was undergoing, but Rutherford took the reports seriously. If the alpha particles were bouncing backwards, they must have hit something hard. But if it happened rarely, there had to be relatively few of them. Rutherford had found the nucleus of the gold atom. Atoms were mostly empty space, with virtually all of their mass concentrated at the middle. The empty regions were the domain of the negatively charged electrons, and the nucleus, the heavily positively charged protons. But there was a problem. The electrons are negatively charged, and the protons are positively charged. Opposite charges attract. The atom should be unstable. The electron should collapse into the nucleus. A large central mass attracting a smaller external mass. Hey, that sounds like the sun and the planets. The sun attracts the planets. They should collapse into the sun, but they don't. Why not? The gravitational force attracting them is balanced out by the centrifugal force of the planet's motion pulling it away. Maybe the same thing is happening in the atom. So the result was the solar system model of the atom, with the nucleus of the sun in the middle and the electrons orbiting outside. But there's a problem here too. The solar system is made up of electrically neutral bodies. When the masses move, they just move. But we've long known that when an electrically charged object moves, it has a fascinating effect. It causes a magnetic field. Moving magnets cause electricity, and moving electricity causes magnetism. Since our planets are electrons and they're negatively charged, if they were to orbit the nucleus, they would create a magnetic field. But the magnetic field requires energy, and that would be drained from the electron, diminishing the centrifugal force. That means that the electron would move closer and closer to the nucleus. The longer it went, the more energy would be drained, and the closer it would come until finally it finished its death spiral, collapsing the atom. The solar system model of the atom is inherently unstable. If it was true, matter as we know it could not exist. But there are electrons, and there are protons in the nucleus. If our best theory didn't work, we'd need a new one, a new theory of the atom. This would just require some clever people looking closely, but the closer we looked, the stranger it got. Stranger and stranger, until out popped something so strange, it was hardly recognizable. So bizarre that Einstein refused to believe it. It was quantum mechanics.